Let's go on a little journey today. We're going to start with a simple arrow, the kind you saw in math class, and we're going to end up right at the heart of how modern AI actually understands the world. We're talking about vectors, and trust me, their secret life is way more fascinating than you probably think.
Okay, take a look at this image. As a human, you and I, we get it instantly. It feels peaceful, right? Maybe a little awe-inspiring. But a computer? To a computer, that's just a bunch of data. So here's the big question. How in the world do we bridge that gap? How do we teach a machine to understand not just the pixels, but the feeling?
And this just nails the problem perfectly. It's what we call the semantic gap. On the one side, you've got the computer's view, a file name, a date, a grid of pixels. It's totally structured, but it's completely meaningless. And on the other side, you've got our human take, the feeling, the concepts, the whole vibe. They're basically two different languages.
Right, and this semantic gap is exactly why old-school databases just can't keep up. You can't just type in a query for show me images that feel peaceful, because the database has no idea what peaceful even means. To solve this, well, we actually need to go back to a pretty basic concept from math.
That's right. It all comes back to vectors. The entire solution hinges on this one surprisingly simple idea, a piece of information that tells you just two things: how much and which way.
But first, let's be clear about what a vector isn't. It's not a scalar. A scalar is just a number, a single measurement. Think about temperature. It's 80 degrees. That's it, story over. Or an object's mass. It's 50 kilograms. There's no direction to it. It's just a value.
A vector, on the other hand, well, it's so much richer. It has that magnitude, the how much, but it also has a direction, the which way. And it's this combo, these two pieces of information packed into one, that makes it so incredibly powerful.
And this table just makes it crystal clear, doesn't it? Speed is a scalar. You're going 40 meters per second. But velocity is a vector. You're going 40 meters per second north. Same thing with mass versus force. One just is. The other is being applied in a very specific direction. And in math, we have a really simple way of writing these down with coordinates. Each number is just a simple instruction: how far to go horizontally and how far to go vertically. It's like a precise little recipe for getting from point A to point B.
Okay, hang on, because this is the big leap. This is the pivot point. We've got what a vector is in physical space, but what if we could use that exact same idea to map out meaning itself? What if we move from physical space to what we call semantic space?
So right, in the physical world, a vector's dimensions are super simple. How far right, how far up.
But here it is, the game-changing question. What if instead of right and up, the dimensions of our vector stood for abstract concepts? What if the first number was a score for mountaininess, the second measured the presence of urban elements, and the third was all about the amount of warm color? All of a sudden, a vector isn't just a point in physical space, it's a point in a space of meaning.
And check this out. This is that idea in action. Look at the numbers for these two images. For the elevation changes dimension, the mountain picture scores a super high 0.91, while the beach is way down at 0.12. But look at strong, warm colors. They're both high, 0.83 and 0.89. See? They're far apart in one dimension of meaning, but really, really close in another.
So we can turn the essence, the vibe of a piece of data into a long string of numbers. That's awesome. But now we have a new problem, right? How do you actually search for meaning when you've got millions or even billions of these things?
It's done with a process called embedding. It works like this. You start with your raw data, an image, some text, an audio clip. You feed it into a special AI model, an embedding model. And what pops out the other side is the vector we've been talking about, also called a vector embedding. It's that array of numbers that has magically captured the data's meaning.
And of course, you need the right tool for the job. There are different models for different types of data. For images, you might use something like Clip. For text, maybe a model called Glove. For audio, there's Wave2Vec. Each one is a specialist, trained to understand the little nuances of its data type and translate it into a meaningful vector.
But here's the catch. A real-world vector might not have 2 or 3 dimensions. It might have hundreds, even thousands. So trying to compare your search query to every single one of those super complex vectors in a massive database, it would be ridiculously slow. It just doesn't scale. The solution is, honestly, it's genius.
It's called Approximate Nearest Neighbor, or ANN. These algorithms are smart. They don't waste time looking for the one single absolutely perfect match. Instead, they find a bunch of matches that are close enough, and they do it thousands of times faster. It's a brilliant trade-off. You sacrifice a tiny, tiny bit of perfect accuracy for a huge gain in speed.
And this is it. If you remember one single thing from this whole explainer, make it this. The mathematical idea of distance, how close two vectors are to each other in this crazy high-dimensional space, is now a direct stand-in for the human idea of similarity. If two vectors are close, their meanings are similar. Simple as that.
All right, let's bring this all home. How is this stuff actually powering the AI tools you're probably using every single day? Because this isn't just theory anymore. It's fundamentally changing how we find and interact with information.
One of the absolute coolest applications is a technology called Retrieval Augmented Generation, or RAG for short. This is the magic that lets chatbots pull in fresh, external information to give you answers that are accurate and up to the minute, instead of just repeating what they learned months or years ago.
And look how simple the process is, now that we know how it works. You ask a question, the system instantly turns your question into a vector and uses that similarity search to find the most relevant little snippets of text from a huge knowledge base. Then, and only then, it hands just those useful pieces to the language model, which uses them to build a really smart, fact-based answer. So just think about the journey we just took. We started with a basic arrow from math class. We blew that idea up to represent the meaning of literally any kind of data. We figured out that finding the closest vectors is just how AI finds stuff that's similar. And now we see that this is the engine running under the hood of game-changing tech like RAG.
From a simple arrow to an AI that can understand nuance and context, the journey of the vector has been absolutely incredible. And it leaves us with this one kind of mind-blowing final thought. Now that AI genuinely has a grasp on meaning, what's next? What complex, subtle, or even emotional concepts will it start to understand tomorrow?